Hi guys, and welcome back to Elevate Chem. I'm Jesse with another concept video. Now this is our last video in our 5-part series looking at stoichiometry. And as always, what we're going to be doing is looking at an actual exam question, because that is going to help improve our understanding, and ultimately that's what you're going to need to do on the day. So the first thing I want you to do is to have a go at this question. Now this is from the WACE 2014 chemistry exam, and it's question 39. So I want you to download the paper, pause the video, and have a go. Fantastic. Now I think this was one of the harder questions that I've seen in a while. It wasn't super challenging, but there were certainly some bits and pieces that made it quite difficult, and it wasn't really one that has cropped up all that often. So I'm going to get cracking into it, and hopefully you can follow along with me. So let's have a look here. There's some text up the top here, which for right now I'm going to ignore. I'm going to skip straight to the question. A, determine the empirical formula of the compound. Okay, I'm definitely going to have to read that text. One of the first things I notice is this question is worth 10 marks. This is a monstrous question, guys, and often they'll actually break it down to smaller components. In this case, they haven't, and they've just sort of thrown you against it, and you have to bear the brunt. So, determine the empirical formula. Well, let's start off with what is the empirical formula. The empirical formula is essentially the simplest and smallest way of representing a molecular formula. So let's say, for example, we might have the formula C4H8O2. The empirical formula would be C2H4O, because it's sort of a simplified version of it. If there's any sort of common factor between it, I could cancel down and get something a bit simpler, and that's the empirical formula. So, how do we go about finding the empirical formula? Essentially, what we have to do is work out by moles what is the percentage of each of these different elements. So, let's read the question. An organic compound that contains only carbon, hydrogen, oxygen, and bromine was analyzed to determine its empirical formula. So, I'm just going to write down roughly what this thing must look like. I'm going to call it CX, where X is the subscript for the number of essentially the fraction of carbon. I don't know what that is yet. HY, OZ, BR, A. So I'm going to need to work out X, Y, Z, and A in order to determine the empirical formula for this compound. So let's keep reading some of the extra information. A combustion analysis of 1.5 grams of the compound produced 1.58 grams of carbon dioxide and 0.563 grams of water. And on treatment of 1.75 grams of the compound to convert the bromine in the compound to bromide ions, and further reaction with silver nitrate, 1.97 grams of silver bromide was precipitated. Now guys, this might not be a long, lengthy bit of text, but there is a lot of content going on here, and a lot of stuff we need to understand. I'm going to tackle this second bit of the paragraph first, because this is dealing with just the bromine by itself. So I'm just going to read that one more time. On treatment of 1.75 grams of the compound, it converts all of the bromine into bromide ions, and further reaction with the silver nitrate, 1.97 grams of silver bromide was precipitated. So we're going to have to assume right off the bat that all of these reactions go to completion. And I'm going to write down what those reactions are. So the first one that we have is reaction that we have, is bromine actually goes straight to bromine ions. I'm not going to put in the states for now. So that's our first reaction, which is covered right here. And then the second reaction is further reaction with silver nitrate. Now, silver nitrate is going to dissociate into both silver and nitrate. And nitrate has a charge of +1. So that means that silver nitrate is going to have Ag plus Br minus goes to Ag Br. So why did I need to write down these equations? Well, I needed to know what the molar ratios were between these substances. And I can see that it's a 1-to-1 and also a 1-to-1 reaction between all of these underlined substances. So that means I can write down as an initial statement, moles of AgBr is equal to moles of Br minus is equal to moles of Br. And the moles of AgBr, well, how can I work that out? Well, I've got 1.97 grams of the silver bromide produced. So that means it is equal to mass divided by molar mass is equal to 1.97 divided by the molar mass of silver bromide. Now again, this depends on the accuracy of your periodic table of elements. The value that I get for the moles of the molar mass of silver bromide is 187.77. Your results may vary slightly, and that gives me the moles as being 10.492 by 10 to the minus 3 moles. Cool. Now what we're going to be doing here for each of these different elements is actually working at the percentage composition. And I always think that's the easiest way to go about this. What percentage mass does it make up? So I know there's 10.492 by 10 to the minus 3 moles of Br, because really that's the substance that I'm actually interested in here. Now what I'm going to do is work out the percentage of Br by mass that makes up this compound. So I'm going to do that by finding out firstly the mass of Br, mass of bromine, is equal to the moles times the molar mass, which is equal to the 10.492 by 10 to the minus 3 that I just obtained, times by the molar mass of bromine. And the molar mass of bromine is 79.904. Again, depends on the accuracy of your periodic table. And that gives me 0.838 grams of Br. So as a percentage mass to mass of Br, that is equal to 0.838 divide by my 1.75, because that's where my bromine came from. That's the 1.75 gram sample of the compound. And then I'm going to multiply that by 100 to turn it into a percentage. And that gives me a value of 47.9% Br. Now that means this compound, whatever it is 47.9% by mass bromine. And the reason why we're actually finding these percentages by mass is because ultimately what's going to happen here, once I work through the question, is oxygen is going to be left as an unknown. So if I can work out all of the other values, I'm going to be able to determine oxygen. So I'm going to keep moving on with the question, and that's all of this second paragraph completed. I don't need to look at that anymore. Back to this first paragraph here. We've read the first section there, so I'm going to continue from the second sentence. A combustion analysis of 1.5 grams of the compound produced 1.58 grams of carbon dioxide and 0.563 grams of water. Okay, cool. So let's have a think about what a combustion analysis is. Well, it means, of course, that I'm combusting something, and the reaction for that is, in general, CXHYOZ BRA. Again, I don't necessarily know, I don't know what these values are, and that will go to CO2 plus H2O plus something else involving my bromine. Again, the key bit here to realize is that it's a 1-to-1 ratio that's essentially happening here. So what I'm going to do is I'm going to work out, again, the percentage by mass of carbon and hydrogen within this compound. And these are steps that I'm going to have to do in order to get there. So first I'm going to have to work out the moles of carbon dioxide and the moles of water. I'm going to start with the carbon dioxide first. So moles of carbon dioxide is equal to mass divided by molar mass. And again, depends on the accuracy of your periodic table, but I get 1.58 divided by 44.01. And this gives me a value of 35.9009 by 10 to the minus 3 moles. Now I'm looking for the mass of carbon. So I need to so I know that the moles of carbon compared to the moles of CO2 is the same. So I'm going to say that moles of carbon is the same as the moles of CO2. And the reason why I can say that is because essentially there's a 1-to-1 ratio. There's one carbon in each carbon dioxide. So therefore, mass of carbon equals moles times molar mass, which is equal to 35.9009 by 10 to the minus 3 times 12.011, and that is equal to 0.431 grams of carbon. Again, I want this as a percentage by mass. So percentage mass to mass of carbon equals 0.431. Now this carbon came from a different sample. It didn't come from the 1.75 gram sample, but instead it came from this 1.5 grams. So I'm going to divide it by the total of 1.5, multiply by 100 to turn it into percentage, and that gives me a value of 28.747% of carbon. Finally, I'm going to do these very similar sort of steps with my hydrogen. So my moles of water in this case, because that's my other combustion product, is equal to mass divided by molar mass. My mass for my water is given here as 0.563. So 0.563 divided by molar mass of water. Again, this might differ slightly for you. 18.01528. I went pretty specific here. Accurate rather. Equals 31.251 by 10 to the minus 3 moles. Moles of H equals 2 times the moles of H2O. And the reason for that is there's two atoms of hydrogen within every water. And that means there's going to be twice as many moles of hydrogen as there is water. So therefore, this is equal to the mass of hydrogen is equal to moles times molar mass. This is equal to 2 times 31.251 by 10 to the minus 3. Again, that 2 is to account for the fact that there's 2 hydrogen atoms within each water. So if I have 31.251 by 10 to the minus 3 moles of water, I have 2 times that moles of hydrogen itself. Then I'm going to multiply the moles of hydrogen, which is what these two numbers when multiplied together give. I'm going to multiply that by the molecular weight, molar mass of hydrogen, which is 1.008, and this gives me 0.063 grams of hydrogen. Now again, I'm going to turn this into percentage by mass. So percentage mass to mass of just hydrogen equals my 0.063 divided by 1.5 times 100, and that gives me 4.2%. Awesome. So I've worked out my hydrogen, I've worked out my carbon, I've worked out my bromine. Well, why can't I actually work out my oxygen? Well, the reason why is because with the combustion reaction, one of the things that I'm adding here, and I didn't write it down, was I'm actually adding oxygen. And because there's this unknown quantity, I can't use the moles of carbon dioxide or the moles of water to determine how much oxygen was present. Instead, what I'm going to do is, because I know the only things present in my compound is bromine, oxygen, hydrogen, and carbon, whatever isn't carbon, whatever isn't hydrogen, and whatever isn't bromine has to be oxygen. So I'm going to say percentage mass to mass of bromine, of oxygen, is equal to 100 minus 47.9 plus 28.747 plus 4.2. And that gives me a value of 19.153% for my mass to mass of oxygen. Cool. So I've worked out by percentage mass. This is what all of the different elements are, all the different atoms. Now what I need to do is actually convert them back to moles. And the reason why is that my empirical formula is based on essentially a molar ratio, not between different molecules, but between the individual atoms themselves. So all of these values I need to convert back into moles. But unfortunately, there is percentages right now, which isn't really that useful to me. But what I can do is pretend that I've got 100 grams of this sample. And by assuming I have 100 grams, that means that all of these values can simply be taken as equivalent grams. So I'm going to assume this is 47.9 grams. I'm going to take this to be 28.747 grams. And I'm going to take this to be 4.2 grams. And finally, 19.153 grams of substance. Awesome. So all I did there was I need to actually get actual masses in order to calculate moles. And in order to get masses, I just pretended that I have 100 grams of sample. And for 100 grams of sample, if it's 47.9% bromine, that means there's going to be 47.9 grams of bromine. So now I need to convert all of these into moles. I'm just going to draw up a little sort of table here. What I have is I'm going to write my carbon up the top, which is 28.747 grams. Carbon, hydrogen, oxygen, bromine. My hydrogen was 4.2 grams. My oxygen was found right at the end there to be 19.153 grams. And my bromine, 47.9 grams. Then what I'm going to do is I need to get the moles of all of these. And if I've got a mass, to get the moles, I need to divide by the molar mass. So I'm going to divide each of these by the molar mass, their respective molar masses, so 12.011, divide by 1.008, divide by 16.00, divide by 79.904, and that gives me these moles, 2.3955, 4.16667, 0.599, and 1.197. So if I wanted to write the empirical formula right now, what it would look like is C 2.3955, H 4.1667, O 0.599, and BR 1.197. Now, I don't know about you guys, but I've never seen a formula that looks like this. We want these things to be whole numbers. And how we do that is we find the smallest value, in this case 0.599, and I'm going to divide each of these values that I've just found by that figure. So dividing them all by 0.599, gives me a value of 4, 7. So apologies, I just wrote down some wrong values there. This should be my 1.197. And this should be 0.599. So that should be my 7. There's 2. And there is 1. Keep in mind, guys, that these are actually approximately equal to these values. They're not actually precisely equal, aside from that last one. We do make some rounding here in order to actually obtain these values here. So that gives me my final empirical formula as being C4, H7, O2, BR. Whew. That was quite a bit of work. Moving on to the next part of the question, B. Thankfully, we can see it's only 2 marks, so it's going to be a lot less work. 1.95 grams of the compound was vaporized and found to occupy 0.387 liters at 95 kilopascal and 105 degrees C. Determine the molecular formula. So what's different between the molecular formula and the empirical formula? Well, the empirical formula is the simplest way of writing it. So C4H7O2Br. And really what we've actually found here is a ratio. We don't know if it's this, or it could actually be C8H14O4Br2, or any sort of multiple thereof. So all I've done here is multiplied it by 2. It could have instead been multiplied by 3. I don't know whether this is the actual formula. And how I determine that is by working out the molecular weight of that compound there. So I'm going to have to do that using the information given in this question. So I've been given a volume, been given a pressure, been given a temperature. I'm going to be using the ideal gas law. So the ideal gas law is PV equals nRT. Rearranging for n, I get n equals PV on RT. Now I have to make sure everything is in the right units, guys. So I've got 0.387 litres, that's fine. 95 kilopascals, that's also fine. But my 105 degrees Celsius, I'm going to have to turn that into Kelvin. So I'm going to get my pressure, so 95.0 times my volume, 0.387. My R is my universal gas constant, 8.314. And my temperature isn't 105 degrees Celsius. It's actually 105 plus 273, or it might be 273.15, depending on how accurate you're being. This gives me the moles as being 11.69 by 10 to the minus 3. So now I need to work out the molecular mass. I'm given an actual mass here. So I can say that N equals M over big M. And therefore, my molecular mass is equal to mass divided by moles. And if I plug those numbers in, I obtain 1.95 divided by 0.01169. I've written it slightly different from up here, but it's the same number. And that gives me 166.76. And guys, keep in mind that this is grams per mole. Awesome. So now what I have to do is compare this molecular weight to what the molecular weight of this empirical formula would be. And I'm actually going to work it up back up here just to save space. So the molecular weight of what I've found just before is 4 times 12.011 plus 7 times 1.008 plus 2 times 16 plus 79.904. I'm going to put brackets around it just to make it nice and clear. And wouldn't you know it, that actually comes out to roughly 166.76. Doesn't quite come out to the same figure, but it comes out very close. And therefore we can say with confidence that the molecular formula is C4H7O2Br, which is actually the same as the empirical formula we found before. Awesome. Jumping to part C. Further analysis of the organic compound revealed that it had a carboxylic acid functional group. Draw a possible structural formula of the organic compound. So the first thing I'm going to do is I'm actually just going to draw in that carboxylic acid because it states in the question that I actually have one of those groups. So I may as well draw that in. There we go. So I've drawn in my carboxylic acid functional group. And now if I look at my molecular formula, I can still see that I have 6 hydrogen atoms left to draw in, 1 bromine atom. I've used both of my oxygens and I still have 3 carbons. I'm going to assume it's the simplest case scenario and just see what happens. I'm going to assume that from here on out, the rest of it is just a straight chain alkane. So drawing in the rest of my carbons, I had 4 in total. So there's my 4 carbons. And if I assume it's an alkane, I'm going to have 1, 2, 3, 4, 5, 6, 7 things left to bond to. And let's start just putting in the rest of the hydrogens and see how many spots I have left over. 1, 2, 3, 4, 5, 6. And then I've got the bromine left over. Just double checking that that's all correct. I've got 1, 2, 3, 4, 5, 6, 7 hydrogens, just like I have in the molecular formula. 1, 2, 3, 4 carbons, 2 oxygens, and the single bromine. I'm going to take a guess that that is definitely a possible structural formula for the organic compound. Now, guys, this was a pretty monstrous question, mostly part A. Look at all of this. It's pretty insane, but it was worth 10 marks. So what I think was potentially a bit challenging about this was there was a lot of numbers being thrown around, and it's useful to actually make it in this nice sort of organized pattern, both for your own sake so you can understand what's happening, and also so an examiner, where they're looking at it, how they can make sure they can see that you're doing clear steps. Now keep in mind, you might not have done this question the same way as me. There were certainly other methods of going about it. Personally, I like to do it as the percentage of mass because it makes me feel nice and secure that I know that I've got the right value. There were a couple of tricks to this question. One of them is to recognize that there was sort of two parts here. There's a combustion analysis and also an analysis for the bromine. That was a little bit tricky potentially. And when it came to your empirical formula, remembering that you have to divide by this smallest number rather than panicking about seeing some of these odd values and producing a very odd empirical formula like that. Remembering that you need whole numbers. The rest of the question, using the ideal gas law to obtain both the moles and from that a molecular weight, which you can then compare to an empirical formula to confirm that it's actually the molecular formula. And finally, using that formula to draw a rough sketch of the compound, given the fact that you know some of the functional groups within there. Fantastic, guys. I hope these concept videos have helped you out, and I look forward to seeing you in some of the later episodes.